Hello, everybody. Got some more to talk about with data today. The other day, we looked at what the machine is doing. For those who haven't had the class yet, the preview of reading binary code for the class where you're actually going to be tested in on that, because that's one of the things that is covered very, very quickly in that class. And then you're expected to answer questions on it with very, very brief coverage. So a few of us instructors decided to start working more of that into other places. So preview mode or a review on that if you've already had the SDEF 120 class or other places where you might get tested on binary. That's what the machine's doing. It's not the most helpful thing for our day-to-day usage, right? We're humans. We don't think in binary or work in binary, and we have to make adjustments to even work in binary. Kind of like we saw the other day, it's too simple for the human mind. So even if we're going to work in binary, we work in hexadecimal, so we work in binary 4 bits at a time. It's just, for the machine to handle it, it's too much of a simplification for our minds. So we kind of complicate it back up to work with it. So not what we do in our daily life. So we want to look at how we handle that sort of data today. And there's another one of those internal storage ones we'll talk about later, week 7 or 8, kind of around the time when you'll have that big final project coming. So I'll need to fill the lecture time, but I don't necessarily want to fill the lecture time with a bunch of things you're going to be tested over, because your focus should be on the final project around week 7 or 8. So something that I like to cover in this class is image data, graphic data, how that's stored internally, because it's not really covered anywhere in the program. But it's images. I don't think the Viscom people even really study the internal workings on that. Right? Like we find the image we need, and what we need to know about is, like, if it's a JPEG, we type .jpg is in the script or whatever where we're trying to use it. We just need to know what, and we just use whatever type we have. So nowhere in the program does it cover the difference between them. What's that internal difference between a JPEG and a PNG and a bitmap and vector graphics, and all the internal workings isn't really covered anywhere. So I like to talk about it somewhere, and near the end in this class seems like a good place, because then it's, you can still focus mostly on your final projects. Well, and it might satisfy some curiosities and stuff. You'll at least hear it somewhere, since not even the graphic designers actually study those internal differences between our graphics types and stuff. So that'll be kind of like the one we were looking at the other day. But today is the much more applicable to our day-to-day jobs in IT sort of approach of data. How do we handle that? So got a few things to look at with that. I should mention this. So to start with, there's here in a little while, I'm going to go over some examples and point out some things you can watch. But if you'd like to follow along and would want to get the software that I'll be using, I guess after we take a break here in a little while, some of it might take a minute to download. So that's probably a good place to start and show you the 2 types of software I'll be using as an example before we end the lecture today. And that way there's plenty of time for it to download while I'm writing stuff on the board. So we're talking about databases, storing our data, and in particular, we want to look at the really highly organized, efficient ways to store data so that we have really, really quick retrieval times for any type of data we want to store. We're going to talk about some of that stuff. So what we would think of when we say the word database. And you have an assignment this week on Access. We're going to look at that here in a few minutes as well, which is a small database. You might want, there are much bigger, nicer ones, including like a MySQL database. So a good place to run that is this software called JAMP. It's a virtual server we're going to talk about virtualization and virtual machines in week 7. That's where it's on the list as assignments and quiz questions and things like that in the weekly lab. So jumping a little bit ahead, but a virtual machine is kind of, you can think of it like a fake machine. So we have like my laptop here running the Windows operating system on the hardware, and that's kind of expensive. I don't want to break it. So if I was experimenting or wanting to experiment and try different things that might break the machine, it'd be useful to have a fake machine that it wouldn't hurt to break. So we can just do a software replica of the hardware part and then install a different operating system on that. And then it's like a fake machine. You can do whatever you want to it. And if it breaks, you just delete it and install a new one because it's just software. We're going to talk about that in week 7. So jumping a little bit ahead, I just let somebody in and didn't write their name on the list quick enough and to forget who it was. But with the powerful databases, those usually run on servers. So we need a virtual server to work with. And one that I'm a huge fan of is XAMPP, XAMPP. That stands for, the X stands for cross-platform. So it's cross-platform, Apache, MySQL, PHP, and Perl. And it also knows Java and Python and some other stuff. So there should be a couple more letters there. But our standard, what's known as a full stack for web application development and website development. The standard full stack server, and this is a little virtual one, I have tested this on all my machines. It will run fine on, works on the, I've tested on Windows machine, the MacBook, Chromebook, Linux machines. I tend to run it on all of them. You don't necessarily need it. I was just, if you want to follow along with what's going on later today, for this one, you just download the installer, whichever installer is appropriate for your machine, and kind of run that. Nothing too fancy about that. I was just pointing you towards which one it was. Oh, and I said the X stands for cross-platform. So there's also a WAMP and LAMP and MAMP that would be more specific for your system if you would prefer that. But the cross-platform one works on all the systems. The other one was a different type of database. MySQL is what's known as a relational database, the stuff we're getting ready to talk about and make some notes on the board. There's also non-relational databases. And for an example today, to look at that, I recently sat down and tried dozens and dozens and dozens of them. And based off what is covered in the curriculum for the courses here at Ivy Tech, our database courses, when I looked at lots and lots and lots of non-relational databases, I thought OrientDB would make the nicest one to segue into based on what's covered here in class. So we'll look at that for an example. If you want to follow along and kind of see what's going on with them, if you just search for OrientDB, Orient Database, that's a NoSQL database, and then download one of these here in the top row, which these are actually all the same folder. Usually we have separate ones for, right? We'll have one link to download the folder with all the Windows stuff, and then another link downloads the folder with all the Mac stuff. But when they first made it, they just went ahead and put it all in the same folder, but that confused people. So they came back to their website and made 4 different links that download that folder now. So they all download the same thing, but go ahead and click the link appropriate for your system, and then it should download fairly quickly. It's not a huge one. And that one is just a folder. We'll have to look at the files, and there's some extra things there. But if you want to follow along later, those are the 2 pieces of software I'll be using. That way you'll have them to follow along, or kind of watch what's going on with it, and then can do the stuff later when there's a little bit more time. Also want to look at access today after we make some notes about databases on the board, because that is the assignment for this week. The weekly lab will have you set up a small relational database, and it's step-by-step instructions walking through Microsoft Access to kind of get started in that. And then some other things. Some people also ask if we could talk about some new hardware and stuff. So I threw that on the list. If there's time today, if not time today, we will work that into the next lecture, because there's also some other big ones coming up soon. Some of y'all may be aware Apple did their announcement yesterday. Was it yesterday or the day before?
It was yesterday.
Yesterday. I know it was this week. So yeah, Apple did announced their new stuff yesterday. But they're not the only company that has new stuff coming out. And after somebody mentioned they wanted to kind of look at some of that and talk about that, which Monday might also be a better, if we have to push that back and talk about it in the next lecture, that might also be better, because then more people will know about it by then. Right now, the only people we know anything about it from is basically the marketing department at Apple. So when like reviewers and other people tech experts get their hands on it, they will write up some information very, very quickly, and we'll have more thorough information over a few days. But Apple's not the only one that does that. NVIDIA is also doing theirs, I think next week. And NVIDIA has, they have a lot on their agenda. They actually have way more than Apple talked about on theirs. So I was also debating on turning that into sort of an assignment, because it's a useful thing to see. But we will get there. I think we will probably have time to kind of talk about that stuff today. But again, if that gets pushed back a day, then after a week, we will know a lot more about the stuff Apple first mentioned yesterday, and can have better conversations about it then too, if we run out of time today. So starting off today, the other day we were talking about data. That's our topic for the week. But what we talked about the other day isn't what most of us are going to do in our daily routines. We want to deal with things at that high level, at the human level of data, not the machine level. So that's where we're going to get into databases. So a couple terms to start off with here, a couple definitions. Database, obviously the one that's going to matter more for us today. So the technical definition of that, like if you go to the dictionary and look up what that word means, is a structured set of data held in a computer. Did the Zoom call just beep at me? Oh, yep. I should turn up the volume a little. I couldn't quite tell if that was a beep on the machine from the Zoom or not. All right. So a structured set of data held in a computer. A little note to put here. Our storage, right? That's where we store our data. Another term that I'm going to go ahead and define right next to database and get these definitions out of the way before we start talking about stuff a little further is data structure. You're much less likely to have heard that word before. In our modern world, you've probably heard the word database, which I think I mentioned at some point this semester, but in case I didn't, data is a Latin word. Means that usually very formally defined as what was given. But informally, we could say the facts, right? Our given facts about things. And data is plural, so there's also datum, which is a singular one. But the main thing is that it's a Latin word, so Latin pronunciation is technically the proper one, data, whereas Data was a character on Star Trek, but a very, very popular character. And a lot of people know that the name of that character. And if you just say data in place of data, people are going to know what you're talking about. They know which word it is, but the technical, it is a Latin word. So we should be using that soft A sound in the pronunciation. Oh, and the other definition here is that a data structure is an organization and management format for efficient access and transmission. And I definitely ran out of room there. Access and transmission. So a big fancy sounding set of words, but just like I did up here, the database, we have that technical definition, but the database is in storage. And a data structure is organization and management format for efficient access and transmission. So that's going to be in our RAM and the CPU, really the random access memory. So database and storage and the data structure and memory. If you're heading into IT, that difference will show up at some point. So there's really, there's two different ones. There's the ones where we store it long-term, our non-volatile storage, the hard drive where it's going to stick around when we shut our machine down, turn our machine off at the end of the day, there's no power going to it. Everything that was in RAM is going to be erased and start fresh next time we power up the machine. So volatile storage is temporary and long-term storage is semi-permanent. Obviously things can happen, but long-term storage is the stuff should stick around for a while. Databases are where we store the data and data structures are where we work with the data. So moving into RAM and then the CPU and through processing and all that. And with that last sentence I just said, there's sort of a key word there that really makes the difference when we're talking about data. And the intention to work with it is what sets data apart from the technical and usable meanings of the word. Because technically anything we store in a computer is data, but we don't necessarily refer to everything as data, right? This video call that you're watching me on right now, the camera picks it up, turns it into a format the computer knows, transmits it across the network. So technically that's data, but we wouldn't really refer to that as data, right? We'd use different words because we're not going to do anything except watch it. And we're not working with it in the computer. We're not going to work with it afterwards. So that technical and colloquial usage of the words is kind of separate there. And as far as a lot of things fit our technical definition of data. Let's look at a quick example. Something popped up in the chat room and I didn't see it. Oh, okay. Let me share the screen. And I'm just going to make a text file. I don't think we've talked about text editors yet in this class, but if you're heading into IT, you're going to want to look into getting a nice text editor to work with. We did talk about ASCII code and Unicode briefly the other day. So a text editor is that super basic stripped down one that is essentially just the Unicode from your keyboard straight into the computer and no extra formatting or anything like that, because that's how we control our machines. So if you're heading into IT, you want to have a nice spot to work with that. There are lots and lots of them out there. I'm using Sublime Text, the Sublime Text Editor, since the last time I did a factory reset on all my machines, which was right before the semester. But there's lots and lots of them out there, and you'll want to look into a few. And my recommendation for things like that is always look, check like best of lists. So it'll go right to a few to start with. But things like this, the 4 best free ones or 15 best. Those are always great places to start because, well, for one, those blogs are going to have links to where you would download them. But there's other stuff in there, like reading through that article is going to tell you, list out the things you want to look for in a text editor and how to make those comparisons. So when you go to look for some, those best of lists are a great place to start, and very different software that way. There's going to be some on every machine. I'm on the Windows machine today, so by default it comes with Notepad. The Mac's going to have Text Wrangler. Is Text Wrangler the default, or do you have to step up to that? Yeah, I think Text Wrangler is the default on Mac these days, but or OS X. But just the basic text Unicode in and out to be stored, how we control our machines. So you're going to want to look for a nice place to work on that. Probably nice, something nicer than the default ones. Something that'll change colors depending on what programming language you're working in or what instructions, what type of data you're storing there. But for now, I'm just going to type some stuff up. Things that could be kind of like information. Get this out of the way. Yeah, the nice text editors will have other stuff. So you can have like that thing that was just in the way, the equivalent of File Explorer, a place to navigate through all the folders. Or on mine here, I can jump right to the default terminal. I think I can jump to more than one terminal. Yeah, I can jump to any of the terminals I have running on my machine, and it's more than just it's still called a text editor, but we still call it has more than just typing text and doing things that way. But a couple sentences here. We've talked about data and information, knowledge, wisdom, that sort of flow. We have spoken language. We can put our information in spoken language form, right? So I'm just making up some names here. So let's say like Bob worked 15 hours this week and makes 23.45 per hour. Sally gets a, I don't know, I'll do something easy to work with math on, 52,000 per year salary, and spent 36 hours in the office this week. Actually, let me turn on a feature I have turned off here. Word wrapping. That way we can see the whole sentence. What are some other names? Again, just making up names. So Becky makes 21.21 per hour and worked 42 hours this week. or David, who worked 33 hours, it's, I don't know, 2, 3, 4, 5 per hour each hour he worked. Oh, 23.45. Let me change up the sentence a little. For each hour he worked. So that's kind of like data, right? I don't need to save that. I don't know why I hit the save button. It has the stuff we need and we can make sense out of it, right? If we know how many hours somebody worked and how much they make each hour, we could figure out their payroll. And I was trying to make those all grammatically correct. I don't see any grammatical errors popping out at me. Typos do happen, but grammatically correct sentences. So it's structured. It's a set of data. And even that technical thing I just mentioned where we could do something with that. We could take those numbers from there, put it in the computer, but that's not really what we would call a database, right? But yeah, actually I can save it. That's why I hit the save button. If I come over here and called this payroll.txt, well, now it fits that technical definition. It's a structured set of data. All those sentences are grammatically correct, so they have a structure to them. And it's held in a computer. I can close it, get it out of memory, and come over here and open it back up from long-term storage. So it fits our technical definition, but we'd never really referred to that as a database, right? It would take a it would take a lot to work with that automatic if we wanted to automate the process. We would need a lot of code for a computer to parse through here and pull out the numbers in order to do the payroll calculations. Oh, that word. Vocab's a big part of this class. So the word parse, P-A-R-S-E, that means to look through a bunch of text and find the part we need. So to read through all this text and then pull out the numbers. As humans, we do that almost instinctually, but when we're dealing with machines, we have to be explicit about it. So you may not have encountered that word before, but it would take a lot of code to read through this particular set of data and find what we need to do payroll. Technically, it fits the definition of database, but not what we would call a database. And yeah, that technical it's what's called a hierarchical database. Still spelled that wrong. We try that spelling the word correctly. Hierarchical database. So it's in a hierarchy, our file and folder structure that we're used to working with. Right, we have a bunch of folders spread out and in different places on the machine. There's some sort of hierarchy to them, and maybe inside of this folder we have a couple of little text files. I think that's what the word, I'll put doc on there. Like the Microsoft Word icon in one of the folders, or I don't know, something with a round icon. We have different files inside of folders, inside of other folders, and we get this big hierarchy. So there is a technical version of that, but we would almost never use that. Even if you're in a setting where you're talking to a bunch of people that know that technical definition, probably still not call it a hierarchical database. You'd say directory structure, or I guess even less formally, just say folders, like we normally do. But there is a technical distinction. So here in the class, we need to list out those technical terms and stuff. Even though we never use that one, it does fit our definition of a database. Usually not what we're thinking of when we say database. It's okay if I erase the board and get into the actual thing we're going to talk about today. So the basic versions of what we actually call database come in two formats. Relational databases and non-relational databases. Or a lot of times we will just refer to them as SQL databases or NoSQL databases. And SQL is the language we use to access them. Sorry, the category of languages. That stands for structured query language. It's how the programming language we use to work with our databases. In particular, relational databases, but a lot of the non-relational databases, even though we use the term NoSQL, they model what we do. The language we do work with them is almost always modeled after SQL, just because that's what database people are used to. That way, the database administrators actually working with the database don't have to go learn something brand new. What they're going to use is very, very similar to the one they already know, which makes it even more just a term. But relational or non-relational databases are two main categories. What I have in SQL and NoSQL. So the one we use that most people think of when we say database is going to be a relational database. I'm going to erase this line and talk about relational databases, and then we'll come back and talk about non-relational ones. So a relational database is for structured data. And when we say structured data, in that definition that I just erased a moment ago, it used structure as in the general English term, not meaning something specific. But when we say structured data, that means something very specific. Structured data is all in the same format, very similar things. So with the relational database, we're going to think about a big table split up into rows and columns, or actually multiple tables. And when we go to put our data in there, we might have things like somebody's name, their age, high school they went to, the college they went to, and kind of like we handed them a form to fill out, right? Everybody fills out that same form, so that no matter how many people we keep records about, we know the same data points about every single person on there. You can think of it like a table. Every cell in that table would be filled because everybody filled out the same form in order to get their data into the database. That's what's meant by structured data. And unstructured data is the opposite of that. It's just the random collection that we can come across. So kind of like all the stuff we could grab about people off social media. It's not a form. People will free to write whatever they want on social media. So we would have different data points about every single person in our database. And if we tried to put it into a table, the table would have more empty cells than full cells, because we wouldn't know. There's more stuff we don't know about people than what we do know. We'll see those situationally before long. But relational databases, when we have those nice full tables, there's some terms that go with these that will be important no matter where you're heading in IT. If you're heading down a data heavy path, it will definitely be important. Now, each particular cell we call a field. Grab some labels. F-I-E-L-D. That'll work. So one cell is a field. I'm going to redraw that table bigger so y'all can see it. There we go. Sorry, that way I'm not trying to like squeeze letters in there, and it's plenty big enough for y'all to read. So every cell in our table or one particular data point is called a field. And a bunch of fields together, put that in red. Would be a record. And that's how our structured data picks up the term relational. So each data point is a field. So each individual data point, somebody's name, their age, the high school they went to, the type of car they drive, all of that stuff gets its own cell in the table or its own field. Then related fields form records. So each row would be about the same person. Those names I made up in that intro example. I think there was a Bob there and a Sally. I think I put Becky. Can't remember what the fourth name I made up was. Maybe it was Dave. Whatever those names were. So we know different data points about each one, right? Like how many hours they work, how much they get paid per hour. I guess that was all we had in those, but each one of those individual data points gets its own field, and then those fields combine to a row in our table to represent a record on that particular item or person in this case. And then we stack up the records. So the third step on this is related records form tables. So you see the relation part is showing up everywhere. And these are important vocab terms. So we definitely want to remember those. And tables are related by common fields. So we're going to have more than one set of data, right? That one of the that I was kind of just talking about, we know the hours they work and how much they get paid. But then there's other sets of data that don't really fit in that nice row, which is going to change every week as they work a different number of hours, or yearly or something whenever they get the raise. That data is going to change a lot, whereas other data would be a lot more consistent. Where they went to high school. That's not going to change ever, right? Once you finish high school, your the records indicating where you went to high school is never going to change. So you might want a more stationary set of data over here. And it does require a little bit of redundancy in it, but we could duplicate, I'll just use yellow since I already marked that here. We could duplicate some of the data that we have in this table, maybe a name field, but really something unique. We want like maybe an extra little number as an ID number to keep track of each individual record gets its own ID. And we could duplicate that data over in another table, and that gives us a way to connect those. And then the biggest advantage of that, if I pull up that little set again, here where I just wrote that stuff down, I have those two tables, then some sort of connection between them. Over here in the file where it was just stored, all our numbers are here. We could find them. It would take a lot of code, but we could put together a script that would automatically look for that stuff and do the payroll calculation off of it. There would just be a better way, might be a better way to do it. Even if we just had something with just their names, right? So like Bob makes 23 per hour and worked 15 hours. Sally makes I don't know, equals 52,000 divided by 52. Oh, I don't know why I just typed that in like a calculation, but some kind of like we saw the other day with CSV files. She's not salary, she worked 40 hours a week. We can have that nice and structured, but we still need all of it, right? If we need the data that's in this file, we need the whole file. Kind of like what we have to do as humans and read that sentence and then pull out the part we need. Even if we had it just a minimal collection in a file, the computer would need the whole file in order to get the data. But relational databases give us the advantage of we don't need all of our data. So if we say no, this piece of data, if we know this, we can follow those relationships around. Well, that field is related to this field, and this field's related to the other table here. And we could go down here and we could find this piece of data from that one we know. We come over here and find this, and we don't need to know our entire data set to find that. All we need is that part to start at, and then we just need to know the relationship between our data. We just need to know how these two fields are related and how these two tables are related. And then that's enough to find any piece of data in there. So we can bypass basically reading in the files, reading in the data. We can skip over most of our database, most of what's in our database, and go right to the data points we know and want, and the ones we want. So it's going to be a lot quicker than if we just had all this data written in files where all we really know is which file it's in, and we have to read through the whole file in order to find it. And that's the idea behind relational databases. With structured data, and when we get into unstructured data where we would have more empty cells than full cells, this really falls apart quick when there's lots of empty cells in there. We can handle a couple of empty cells, but not very many. So it's like a form. We want everybody to fill out the same form. And then we go type that into our database and we know the exact same data points about everybody. So our table's nice and full and we can follow any of our relationships around to quickly retrieve data. That's what we usually think of when we say the word database, right? Those highly organized things that are going to be really, really quick, or we'll have millions of records in a database, and we still expect to find any piece of data we want in a couple of milliseconds. The really quick things. That's what we're usually thinking of when we say database, our relational databases, or our SQL databases, the structured query language. So that's the structured part of it. The language, that's just, you know, the encoding we're using to work with that database, or what symbols from the keyboard we use in order to work with the database. So that part's easy. Query, you may have heard the word before. Query is a criteria-based question. I wanted to try to fit that on the board somewhere. It looks like I'm out of room, and that's the last thing I was going to put on the board, isn't it? I guess I have to erase some stuff. It's okay if I erase this label over here.
I'm good.
I had one more word I wanted to write on the board, and it's just not quite going to fit. So what a query is a criteria-based question. Probably could have squeezed that on the board somewhere, just not legibly. But another one of the important definitions. So the example, for an example, a normal question might be something like, can I get a steak at Applebee's? I think everybody knows that's a yes, but regardless of what the yes is, it's a very general question, right? We want, there's no criteria in it. There's nothing to narrow that down. So turning that from a question into a query might be something like, can I get a steak at Applebee's for under $12? There's that extra low criteria. In that case, a price criteria, an upper limit of what to pay for a steak. And that's the difference between a question and a query. And in order to do the whole relational connection thing there, the computer will need the criteria so that it knows which relationships to follow. Because just all of them usually isn't good enough to narrow things down. And with non-relational databases, and all of this happens in storage as well. So all of this is over on the hard drive. So when I say we don't need the whole database, like the whole database is over on the hard drive, right? Maybe a huge database taking up several terabytes of storage space. But when we go to work with it, we need to move it over to RAM and CPU and registers and all those pieces we talked about last week. And several terabytes of data is not going to fit on pretty much any RAM chip, right? That'd be a seriously impressive computer if you could fit several terabytes of RAM, several terabytes of data into the RAM. So we need to cut that down to just the parts we need. Where that one data point we know that we're going to base our criteria off of to start things, that's a really small piece. So that'll easily fit in RAM. And then all we need to know is these small relationships. And then the result of that is all we need to load into RAM and the CPU. So most of our data stays over in storage and we never actually load it into the processing part. And earlier I mentioned data structures, the ones in RAM, once we get it there and how we work with it. So a very common theme in our non-relational databases, that word's already erased from the board, I'm not sure why I tried to point at it, or the NoSQL databases, is we know that when we get it over into this, move it to the CPU to work with it, we need it in certain forms. So why don't we just go ahead and store it in that form? And that's a very, very common theme. And then we usually look for optimizations as far as which form to use. Are we most concerned with how it's organized and how to keep it straight? There's different ways the machine can optimize for organization. Or we could organize it for speed, optimize the speed. What's the best way to get it into RAM, through the CPU, and back out to the output as quickly as possible with minimal usage of our hardware? Or for speed, the fastest. And they're not always going to line up. My notes, I wrote down some examples. Well, some of y'all are heading into software development, so you'll need to know these words, but just to list them off. So like if we want to optimize for how we organize it and how we store it long-term, we might use things like sets and lists or vectors, even maps. If we want to optimize it for the RAM and the CPU, for how much demand we put on our physical hardware devices, we would probably set it up as stacks and queues. And there's a few others you use with. Or we might be solely concerned with how fast it happens. What's the best way to get it in and out as quickly as possible? In which case we'd use things like trees and graphs. The NoSQL example I had in mind for after our break today is a graph one. So it's one that's optimized for speed. And it is fast. After I dug through dozens of them and was showing it to other instructors and IT people around Ivy Tech, and was like, yeah, I think this one's a great way to make a segue, since everybody's going to study relational databases in that class that's required on just about all of the programs, the DBMS 110 class, and learn SQL. This particular graph-based database is a great way to transfer over. And as I was showing it to people, all these computer experts were like, wow, that's fast. It was, it's optimized for speed. Everything about it is to do it as quickly as possible. So a graph-based database, and we'll see a little bit in that name, not graphs like you're used to from the XY plotting, high-level math graphs, modern math graphs, which look more like a spider web. We'll see that in a little while. And then we have lots of choices depending on what's most important to us for the non-relational data, different ways we can store it. And also that file that I used as a really bad example of data storage, technically that we could use something like that. That would be a NoSQL database because our data is stored there. There's a way to get to it. Just wouldn't be not a very good way. So usually we use the word database when we're talking about good ways to store our data. And obviously that's going to be specialized to the case we're working with. What are we doing in particular? So we'll look at one case of that. But the big one is going to be relational databases. So we're going to spend a few minutes looking at those, including the one your homework assignment's on, but it's probably a good time for a break, right? That finishes most of the writing on the board, and now we can click around on the computer and do stuff. But before we get started into that, does 10 minutes sound good to everybody? Or
yes.
Okay, I heard a guess real quick. So let's, it's 1:54. We'll get back to it at 2:04. I'm gonna go grab a cup of coffee, and I will see y'all in just a moment.